what does it really mean for an AI to think? Today, we're diving deep into Kubernetes, the strategic compute fabric. The cloud native era requires a compute substrate that spans environments. Kubernetes is that standard, orchestrating 88% of container workloads used by 5.6M developers. It unifies public clouds, private data centers, and edge behind a declarative API. Platform engineering teams harness it to deliver self-service infrastructure, resilience, and portable deployments. It's not just orchestration, it's the operating model for modern software delivery. It defines the operating model for modern infrastructure. What this slide communicates establishes Kubernetes as the dominant universal orchestration layer and a strategic enabler for platform engineering, portability, and delivery velocity. But here's where it gets interesting: the orchestration gap. Infrastructure is more fragmented than ever: multi-cloud, hybrid, edge. Manual runbooks and scripts produce snowflake environments. Outages cascade. Legacy configuration tools, Chef, Puppet, Ansible converge state at runtime, not continuously. Drift goes undetected until failure. Recovery is measured in hours, not seconds. Scaling microservices amplifies these gaps. Operators spend 30–40% of time on toil. A fundamentally different approach is required: continuous, automated state reconciliation that operates without human intervention. Legacy methods are collapsing under the weight of modern distributed systems. What this slide communicates identifies the failure of imperative, periodic configuration management at scale, and the urgent need for continuous, self-healing orchestration. So what's the real problem? Let's talk about the complexity ceiling. Microservices architectures introduce hundreds of independently scaling services. Imperative commands obscure dependencies. State is scattered. Human operators cannot manually track health across thousands of ephemeral pods. Each service requires scaling rules, health checks, recovery procedures, becoming an exponentially growing operational burden. Without a unified control loop, entropy dominates. Teams drown in alert storms and manual restarts. Complexity grows superlinearly with the number of services. What this slide communicates shows how microservices scale operational complexity beyond human capacity, creating an entropy problem that imperative models cannot solve. This raises a critical question: the declarative model, a paradigm shift. Describe the desired end state, not the procedural steps. Kubernetes controllers observe current state, compute drift, and reconcile continuously. Self-healing is built in: restart failed containers, reschedule on node failure, auto rollback unhealthy deployments. The same manifests execute identically on any certified cluster, AWS, GCP, on-prem, enabling true workload portability. Infrastructure becomes version-controlled YAML, auditable and repeatable. This model transforms ops from manual reaction to automated convergence. GitOps extends this by using Git as the source of truth for desired state. What this slide communicates introduces the declarative continuous reconciliation breakthrough that eliminates drift, enables self-healing, and makes infrastructure programmable and portable. Now let's zoom in on the Kubernetes control plane. API server, central hub, RESTful, handles authentication, authorization, admission. At distributed, Raft consensus, key value store. The single source of truth for cluster state. Scheduler filters nodes by resource requirements, affinity, anti-affinity, taints, scores for optimal bin packing. Controller manager runs control loops, node controller, replication controller, endpoint controller, each reconciling actual versus desired state. Kubelet node agent ensures containers match pod spec, reports node health, Kubeproxy manages network rules, enabling service abstraction. Together, they form a continuously reconciling distributed control system. What this slide communicates lays out the core architecture, the control plane components that implement the declarative reconciliation loop at scale. Here's something most people overlook: standardized primitives, pod, atomic scheduling unit, shared network namespace, and storage. Service-stable virtual IP and DNS load balances across labeled pods. Deployment manages replica set, rolling update with maxsurge.mocktefern versioned history. Config map secret, inject configuration as environment variables or volumes decoupled from image. Persistent volume claim, request storage abstractly, EBS, NFS, Ceph, stateful set, ordered, stable identity, and persistent storage for stateful apps. Daemon set ensures a pod runs on every node. Together, they form a composable application model. These primitives are the vocabulary for defining cloud-native applications. What this slide communicates defines the composable, declarative building blocks that abstract infrastructure and create a consistent application model. Think about this for a second. The deploy workflow. Declare kubectl apply f deployment.yaml desired state sent to API server. Persist etcd stores spec. Schedule. Scheduler assigns pods to nodes, respecting constraints and scoring. Execute. Kubelet instructs container runtime to pull images, start containers. Observe. Controllers monitor. If a pod dies, a replacement is created automatically. Scale horizontal pod autoscaler scales replicas based on CPU, memory, or custom metrics. Vertical pod autoscaler adjusts requests. Update, rolling update progresses gradually, checking readiness probes and respecting pod disruption budgets, ensuring zero downtime. This automated pipeline delivers predictable, repeatable deployments at any scale. What this slide communicates walks through the end-to-end deployment lifecycle from declarative intent to automated execution, scaling, and zero downtime updates. And this is where things get complex. Networking, universal connectivity. CNI plugins define the pod network Calico, BGP network policy Cilium, eBPF, encryption, Flannel, simple VXLAN. Service types, cluster IP for internal, node port for external via node IP, load balance provisions, cloud load balancer. Ingress, layer 7 routing, host dot rules, TLS termination. Service mesh, Istio linkered, adds sidecar proxies for mutual TLS traffic splitting. Distributed tracing. Network policy enforces zero trust segmentation. Default deny, explicit allow. This unified connectivity model spans clusters, clouds, and on-prem. This model enables secure, observable communication across any environment. What this slide communicates shows how Kubernetes provides a universal, programmable network fabric from pod-to-pod communication to external ingress with integrated security and observability. But here's where it gets interesting: security by default. Least privilege RBAC. Roles, cluster role bindings restrict API access. Network policy enforces microsegmentation. Deny all by default, explicit allow. Pod security admission enforces privileged baseline restricted profiles, blocking insecure pods. Workload identity, service accounts mapped to cloud IAM roles via IRSA OIDC, eliminating long-lived secrets. Supply chain, image signing with SigStore, verified by admission webhooks. Policy engines, OPA gatekeeper enforce compliance as code. Mutual TLS via service mesh encrypts all east-west traffic by default. A secure supply chain and zero trust posture are now defaults. What this slide communicates demonstrates how security is embedded into every layer, identity, network, admission, supply chain, making zero trust the default operating model. So what's the real problem? Let's talk about platform engineering impact. Deployment frequency surges from monthly to multiple times per day. MTTR shrinks from hours to A5 minutes through auto healing. Developers self-serve golden path templates, CI/CD pipelines, ephemeral preview environments. Operations transforms into platform engineering, curating internal products, not maintaining snowflakes. Consistent multi-cloud substrate eliminates vendor lock-in, enables cost optimization. Business outcome, faster experimentation, accelerated time to market, improved developer satisfaction. Platform teams measure success in developer throughput, not server uptime. What this slide communicates quantifies the transformative impact on delivery speed, reliability, team autonomy, and business agility, shifting ops to platform engineering. This raises a critical question, extending the horizon. Edge computing, K3s, and micro K8s run full Kubernetes on ARM, IoT, 5G MEC, AI GPU scheduling via NVIDIA Operator, Kubeflow for ML pipelines, KF serving for inference. Serverless. Native delivers scale to zero, event-driven auto-scaling on Kubernetes. Multi-cluster cluster API manages cluster lifecycle. Karmata, fleet schedule workloads across clusters. The control plane extends to databases, operators for PostgreSQL, MongoDB, and streaming, Kafka. Custom resource definitions allow domain-specific APIs, extending the platform. Kubernetes absorbs new workloads without re-architecting the platform. What this slide communicates reveals Kubernetes expanding beyond containers to edge, AI, serverless, and multi-cluster the control plane, absorbing all workloads. Now let's zoom in on the universal control plane. Kubernetes has become the operating system for distributed systems, abstracting compute, storage, networking. Operators extend it to manage databases, message queues, and observability stacks declaratively. The ecosystem innovates at incredible velocity, new CRDs, controllers, mesh features. It's the integration plane for infrastructure, security, and delivery. The strategic question is no longer whether to adopt Kubernetes, but how to build a differentiated platform atop it. The companies that master this will lead the next decade of software. It is the foundation for the next generation of infrastructure engineering. What this slide communicates positions Kubernetes as the kernel of the modern data center, an integration plane for all infrastructure services, and a strategic imperative for any platform strategy.